Then during the midterm exam week, I'd like to move our midterm exam to the October 21st in the classroom. Okay. So also, I'm thinking the change the schedule of exercise lab 4, which is scheduled on the October 12th, but a little bit earlier next week. Okay. But I don't decide that. I will let you know at most by Monday. So because we'd rather have the early exercise lab to have a time for you guys. The due of the project A is October 18th. Okay, but midterm exam is changed to the October 21st in the classroom. So it's the same time as the class hour, and that will cover chapter 1 through 6. Okay. The coverage is the same. I think that this week the lecture will be part of the midterm exam. And exercise lab 4, I'm thinking the October 7th, but I will announce on the next week. Okay. And also today, I asked the GA at the end of class, it's the 15 to 20 minute presentation about your Project A. So he will explain how you guys can do the first project, which is due on October 18th. Any question regarding to the schedule? Okay. Yes. Which one? I cannot hear you.
I told you after class about the midterm.
This one, midterm exam, is not after class, in the class.
No, can I talk to you after class?
Regarding to the exam, okay?
I mean, we're going through the homework, like homework one.
Jay, let me know if 15 to 20 minutes before class. So we are talking about the CPU scheduling, the first come first serve. And anyway, any scheduling, CPU scheduling algorithm are based on the priority. But problem is what kind of priority we are going to consider. The first come first serve, arrival time is the priority. Okay? There's no difference between the preemptive and non-preemptive in case of the first come first serve, because anyway, the arrival time will be considered. And the second thing is the shortest job first. The priority is the amount of CPU burst time. That is the priority. The shorter will be higher priority, will be selected. There are two options. One is the preemptive, another one is non-preemptive. Non-preemptive case, once the process starts to be running, then it will be terminated no matter what happened, like including interrupt or the new processes coming in and process move back to the ready queue. No, we don't consider such an event as the non-preemptive case. However, non-preemptive case, you can stop in case of the event that we have learned. 4 different cases, like moving from the running queue to the wait queue, or the new process in the ready queue. At that time, stop, then running. And also we have learned the shortest remaining job. Okay, shortest job consider the CPU burst time when the process is entering the ready queue. But remaining job will be decreased as the processor is running in the running queue. Okay, so we have learned the 3 different algorithms. Then today we are going to continue the priority scheduling. So priority scheduling, we specify explicitly the priority for each process. Just like the shortest job first, we have the 2 types of the priority-based scheduling algorithm. One is a non-preemptive, which means once this one is a start and end, no matter what happened in the middle. However, preemptive, the stop in case of the event like in this case, new process arrive to the ready queue. As I strongly suggest to manage ready queue and running queue time and Gantt chart. Using this one, you can avoid any mistake of definitely this one will be the big part of your midterm exam, definitely. Okay? At least 20% of the midterm exam will be the CPU scheduling algorithm. Oops. So, first, preemptive, non-preemptive case. So at time zero, process 1 is alive, okay, with the CPU burst time the 19, and the priority is 3. How many processes in the ready queue at time 0? How many processes are in the ready queue? How many? 1. So will be selected no matter what. Oops. That's it. Okay. So in the ready queue, process 1 is alive, the 0, 19, 3. We are going to consider this one as the priority. Okay, it's a explicitly priority. So time 0, this will be selected. P1 is in the running queue 3. Okay. Then at time 2, P2 is alive. The 2, 10, 2, but it will not be stopped because it's a non-preemptive case until P1 is completed. That is a 19. Okay, P1 takes the CPU resource. Okay, please pay attention to the lecture. Okay, if you guys want to talk, you can leave. Okay, you can leave. It's okay. If you guys want to talk with the other or discuss, you can leave. Okay. P3 alive the time 4, 7, and 1. Then until time 19. Okay. Then it will be terminated. The next one is the highest priority, that is the lower number of priority. Okay? We are going to use the 0 as the highest priority, and the higher number is the lower priority. So then P3 will be selected. Then next one is P2. Okay? So that is the non-preemptive. We can calculate the waiting time and the response time. In case of non-preemptive case, waiting time and response time are always the same. Because in the middle, there's no waiting time per process. So what about the preemptive case? Preemptive case is a little bit more complicated. So time 0 is the same as the non-preemptive, but when P2 is alive, and then with the priority 2, then P1 is still priority is the 3. So P2 will be selected at the time. So P2 moves to the running queue with the priority 2. Then time 4, P3 is alive with the priority 1 and P2, 2. So P3 will be selected. So P3, so priority 1. So P3 is the highest priority. So we'll take all the CPU resource until terminated. That is the 11 because the CPU burst time is 7, 4 to 11. Then from the ready queue, P2 will be selected, followed by the P1. Okay, that is a non-preemptive case. So we can calculate the waiting time. As you can see, waiting time compared to the non-preemptive case is much better. Why? Because we are going to stop the processing in the running queue. So in case of a preemptive, so waiting time will be the highest priority will be selected. The waiting time is in terms of waiting time, it will be better. So this is the priority based. Next one is a round robin. Round robin, we are going to make the time slot, then assign per the process, each process, then take turn. As name implies, it's a round robin. At that time, such a amount of time of each time slot is the time quantum. Depending on the time quantum size, like the time quantum 1, 2, 3, or the big, the 100 millisecond. So there are slightly different characteristics we will see. Okay, so first, so this is our process list P1 through P4. So CPU burst time is 53 for P1 and 17 for P2 and so on. At the time, we are going to use the time quantum 20. So this timeline will be divided by the 20. Then, so P1 first, the 20. And next P2, 20, but they need only 17. So we don't have to waste the 3 time slots, so just the 17 and terminate. And next one this, and next. We can take time. This is the round robin. However, what if we increase the time quantum as the 100? What about the Gantt chart with the time quantum 100? Same as first come, first serve. Okay? So that means if we have the very large time quantum, that will be first come, first serve, default start. What if the smaller size of the time quantum? What is the benefit? All process will get the chance first time use the process, which means less response time. So if you need such as online transaction processing system, the banking system, or the Amazon site or bidding site such as eBay, those websites need very quick response time. Okay, at that time we can use such a lower, smaller the time quantum. Okay. Then using the different size of the quantum size, we don't have to implement separately. We can use the round robin as the first come first serve, or the response time, the CPU scheduling algorithm. So far we have discussed the first come first serve, should is the first, should is the remaining the first, priority, and round robin. And also some of them has the 2 options, preemptive and non-preemptive cases. However, each one we cannot say which one is the best algorithm. Depending on the characteristic of your system, sometimes round robin is better than the first come serve. Or if your system is batch job system, like the data warehousing system, the first come first serve is more important. So we cannot say which one. So also, sometimes your system require very fast response time, but during the night it needs more throughput. So their characteristics can be changed. So can we address such the different various requirements? So to address that one, so we are going to use multi-level queue, which means we have not only just one queue, ready queue, we have multiple queue. So each queue has their own scheduling algorithm. Suppose that we have, so this queue is the round robin time quantum 8. This queue is the round robin time quantum 16, and this one is a first come first serve, something like that. So we are going to accommodate the different requirement using multi-level queue. So for example, this is a typical example of any operating system, like the system process, interactive process, and batch process, student process. This one requires very fast response time. This one is not very high priority. So we have the different requirements. So we implement the Q1, Q2, Q3, Q4, Q5. For this one, we use a round robin. Time quantum is 1. And this one, first come, first serve. We can assign different. Problem? How many processors do we have at this time? Let's say 1 processor, 1 CPU. Can all queue utilize the CPU at the same time? No, because we have only 1 CPU. So which means we need to schedule along the queue. Which one will be selected? round robin or the priority. In this case, we can consider the priority also, or we can consider round robin. So first, which queue will be selected. Then, for each queue, apply its own scheduling algorithm. 2 times, 2 rounds of the scheduling algorithm. Okay? So that is the problem of, that's the first problem. Another problem is, how do we know this process is for student process? This is for system process. It's obvious in this case. Sometimes it's hard to say this it need the highest priority. This need lower priority. We don't know. So to address that problem of the multi-level queue, we are going to propose multi-level feedback queue. It's similar as the multi-level queue, but like this one, we have the multi-level, but they are connected, which means always process enter the first queue. Okay, this is the input. Okay, this is the input, and this is the only output. Then the output of the first queue will enter second queue. Then, consequently, the output of this queue going to the third queue, and finally terminated. Then, this one has the algorithm that provide fast response time, such as round robin 1. Okay, which means as long as the process enter the ready queue, then select it with the round robin 1, which means within short amount of time, any process will get the CPU resource, fast response time. Then if that is terminated, then terminate. Otherwise, going to next one. Next one is round robin with longer time quantum, like the 4. If that is terminated, then terminate. Otherwise, going to first come, first serve. Then eventually, so it's kind of filtering. Okay? In this filter, only short amount of time process, and that need fast response time will be completed. Otherwise, move to the next one. The last one usually first come, first serve, which means anyway it will be terminated. So this is the multi-level feedback queue. Okay, let's see the example of the multi-level feedback queue. I think I have some example of the multi-level feedback queue. Oh yeah. Okay. So let's say this one was used for the previous project. So to understand the multi-level feedback queue, I made this slide. So let's say we have the 3 queues in the multi-level feedback queue. The first queue is the round robin with the time quantum 8. We pretend that this one is the scheduling algorithm that provides a fast response time. And 16 means it's a longer time quantum. It close to the first come, first serve. The last one is first come, first serve. Also, anyway, this is a multi-level queue. We have the only single processor, which means we need to schedule along the different queue. our scheduling algorithm is a priority-based scheduling algorithm, which means highest one, the first one will be highest priority. So this one will be selected in case that there exists a process. If there is no process, then next one. If there is no process, the first one and second queue, and last one will get the CPU resource. This is our multi-level feedback queue. So suppose that this is our process list. So process 0 to process 9. So process 0 entered at time 2. CPU burst time is at 10. So this will be processed at the Q0. Okay. Then time 8, the new process arrived, which means this one is the higher priority. So there are two options also, preemptive and non-preemptive of the round robin. Preemptive case, it will be stop and select a new one. So we are going to use the preemptive case. So this one is a lower priority. Okay. No, this is the round robin. So next one will be selected. So P0, okay, time 10, and it will be, this is a round robin. Okay, this is a round robin. So P1 is entered, but still P0 takes the time quantum, that is the time slot 8. Okay, so it will be the 2. The remainder time is 2 because the process 0 takes the 8 time, the 1 time quantum, which means the 8 time slot. Okay, then move to, because it's not terminated, move to the next queue. Then this Q0 has the process, any process though, so it will take the CPU resource. So P1 will be the next round, next turn. Okay, then this one will be terminated because it has only 7 CPU burst time. Okay? Then there exists the processor still Q0. So P2 take the 8 time slot. Okay, it's a time quantum 8. Then move to the next one. So there's no processor in the Q0, which means Q1 take over the CPU. So that is this time the P0 is the first, then terminated, because it needs only 2. Then next one is a P2. It will take the 16, supposed to be 16, but the P3 enter the higher priority queue. So Q0 take over the CPU resource, okay, and do the same thing. Then it's not terminated, still need the 24 and move to there, and there's a new process, the P4. So P4 will be terminated because it needs only 5. Then Q1 will take the CPU resource, then running, but there's another process in the Q0, then Q0 will take the CPU. Then run the round robin with the time quantum 8, then take now the 8, then move to the Q1, and continue the disturb. Then if there is no process, then we will process the Q1. There is another process, same thing. Then even though we process the time quantum 16 for the P5, it's not terminated. So then move to the next one. Finally, this is the first compressor. It will be terminated eventually. Okay? Then we can do this. So as you realize, the process that has the smaller amount of the CPU burst time can be completed in the first 1 second queue. Otherwise, if the CPU and the processor has longer, the CPU burst time will be terminated at last. So it's kind of filtering the multiple level step. So only using the CPU scheduling, so we can do this one. Problem, benefit, as we have seen, it can address the multiple characteristics of the process or system. Problem, I don't think you guys can understand right away this algorithm, me either. So it's complicated. So in the CPU scheduling algorithm, I think one of the students last time asked a question, what if, in the afternoon class, what if during the processing of the CPU scheduler, what operating system can do? Nothing, actually. So just waste of the CPU time. So which means we need very simple, very fast CPU scheduling algorithm. Even though it can address the multiple characteristics of the process, but it takes a time to process. It's a latency. It's a waste of the time. So we need to be careful whether this one can be used for our scheduling algorithm. That is a multi-level feedback queue. So it's a flexible, but it's a very complex. That is the issues to use in the real life system. Okay, think about the ABS. What is the ABS? Anti-braking system. You know what is the latency? Allowed latency? It's a couple of milliseconds. You need to detect whether it's not balanced the left-hand side, right-hand side, but if it takes 1 second or 2 seconds, within a second you hit the other side and sleep. So at that time we need a very simple but reliable scheduling algorithm. Okay. What about the thread? So far we have discussed about the scheduling per process. What if the thread? Thread means one process may have several threads. Also, thread, there are two types of thread. One is user thread, another one is kernel thread. So in case of user thread can be managed by what? User application, user process. So once we schedule the process, within a process we can schedule thread. Which thread will be assigned to each CPU processor. So that is called the process contention scope. Okay? So we can schedule per thread within a process. Okay? Within a process, we can schedule specific thread. Okay? This process also can be scheduled by the previous approach. However, kernel thread is slightly different. Not slightly, it's totally different. Why? Because as we have seen, we have the user thread, but in the kernel can be multiple, but we cannot guarantee whether this is the dedicated, sometimes it's many to many, and sometimes it's many to one, and so we can schedule separately kernel thread, not like the user thread. Okay, that is called the system contention scope, which means altogether the kernel thread should be the schedule. Okay, unlike the user thread. Okay, that is the threading, the scheduling for the thread. What about the multiple processor? Multiple processor, how many? We have many. The processor. There are different types of the multiple processor. One is the SMP. SMP is a symmetric multiprocessing, which means each process acts as the same. Okay, it's a symmetric, which means that processor, CPU, is its own chip. Sometimes it can be dual core. Then they share the same memory. It doesn't matter whether this processor first assigned to here, assigned to here, assigned to Y, it's a symmetric. That is a symmetric multi-processing. At that time, so there are two types of the affinity. Affinity means this process is assigned always a CPU 0. Why? Because in the CPU there is also cache area. So if we keep the data in the same, so it's a hard affinity. It will be better performance. However, to assign this one, what if this CPU is very, very busy and the others are idle? If we can assign to this, then it will be running. However, if you keep the hard affinity, should keep waiting until this one is available. So soft affinity can be scheduled for each. Also, each processor has their own latitude scheduling. Okay, so they can use their own scheduling algorithm, different scheduling algorithm, or homogeneous scheduling algorithm. It doesn't matter. So that is the multiple processor scheduling. Issue is the NUMA is the non-uniform memory access. In this case, most of the SMP is access the same memory. It's a common memory. However, another type of the multiple processor system is they share nothing. Each CPU has their own memory. Problem, they cannot access the updated data in other memory. So, to address that problem, the NUMA architecture actually provide the functionality to access the data in other memory, other system. But this one is slower. So in the scheduling algorithm, you need to consider whether your processor accessing only this data or other data in the memory. Okay, data in other memory. So it's more complicated. We are not going to discuss about the scheduling for the NUMA or such as shared nothing multiple processor system. Okay. Another issue in the multiple processor scheduling is load balancing. As I said, what if this one is busy and the others are idle? Then what if we move the process in the ready queue to others? In case of the software affinity, you can do that. There are two types of the migration. This is called the migration. One is a push migration. Push means in terms of this CPU 0, which one is busy, push out to others. Okay. Another approach is a pull. If you believe that this process I'm idle, my capacity is still utilization is 10%, 90% are idle, then you can pull out from the busy one. So that is a pull migration. Can be used to balance the CPU workload. So you can consider that in addition to the CPU scheduling algorithm. In multi-core processor, multi-core system is in one chip we can process multi-thread at the same time. We can view as this multi-core system as a multi-processor system. Okay, at that time, when we can consider the thread as a two types, as we have seen the beginning of this semester, beginning of this chapter, two types of the job. One is I/O bounded job, and another one is a CPU bounded job. CPU bounded job is mostly operation, the calculation. On the other hand, the I/O bounded job is I/O wait. So we can utilize the time for I/O wait for another CPU, another processor CPU. Similarly, in the multi-thread programming, multi-core system, so utilize such a multi-thread approach. So there are two types of the CPU at the instruction cycle. One is the computation, and another one is it's kind of I/O way, but it's accessing the memory. So that is called the memory store cycle. There are two different. The cycle, one is the computation, another one is the memory accessing. So during the memory accessing, we cannot do anything. So why don't we utilize that one iteratively? So there are two threads. This one is in the core. Okay. So in one core, we can process two threads at the same time. So because of that, this is called the logical thread, logical core. So even though physically we have the 4 core, or in case of quad core, 8 core system, 8 core, logically we can process 16. Logically 16 core because of the such a changing the take turn in case of the memory store cycle. Okay? So it's logically there are two threads. Physically, even though we have one, it can be two or three. So much more than that. So by considering that, we can actually get the full benefit of the multi-threading in the scheduling also. Okay. There's another interesting issues that is real-time scheduling. Nowadays, the real-time scheduling is getting important. Think about I think that in 2020, until the 2020, the U.S. Department of the Transportation, they require all the vehicle keep the some sensor between the vehicle. Like if something happened here, the car in front, they send the signal, sensor, data, so something the accident, then this car can be automatically stop or slow down. So this kind of the device, somebody said this is a vehicle-to-vehicle network. V2V network or something like that. It's nothing but the sensor installed, equipped for the vehicle. So all vehicle, if all vehicle has such a sensor, I'm not sure whether that works perfectly, but hopefully that will help to reduce the accident or to avoid any unexpected situation. But the key problem is how quickly the sensor detects and how quickly sensor inform to other vehicle. Okay, so even though you detect the accident, but it will take the 10 seconds, then it's useless. So at that time we need real-time operating system, real-time sensor, and the main part of the implementing such a real-time system is a real-time scheduling. At that time, what does that mean, real-time? Not fake.
Low latency.
Low latency. Close, but not exactly. Many of the students, even in the computer science, believe real-time system, real-time operating system. Real-time something means fast or low latency, but not always. In other words, for example, like the sensor to detect the nuclear plant, or the accident, or the smoke detect. So the faster is the better, but how fast? So we should have the policy. So within 1 second, within 1 millisecond, the vehicle sensor detect the next car accident, then inform to other. So policy. So real time means guaranteed, meet the deadline. Okay? Usually deadline is very close, right? So that because of that, we believe the real time means a fast, but not just a fast, it's a guaranteed or meet the deadline. So that is a real time operating system. How can we implement such a real time operating system? Key part is the real time scheduling. Okay? There are two types of the real time. One is the soft real time. Soft real time means we try to do our best to meet the deadline. But not always, sometimes it can pass the deadline. On the other hand, hard real time means always 100%. It's a meet the deadline, guarantee within the given time. This one will be used for critical system. This one may not, right? So like this smoke detector, probably hard real time, and nuclear, the plant, the detect or the vehicle is a hard real time system. There are two types of the latency that we can consider. In previous algorithm so far, we didn't consider such a latency. At the context switch, we ignore. Or any other, the scheduling itself, the latency, we ignore. Because we want to focus on the algorithm itself. Right here, when we implement a real-time, the CPU scheduling algorithm, there are two main latency. One is the interrupt latency. Interrupt latency means once event happen, okay? First thing you need to interrupt, okay? You need to activate the monitor. You need to inform to your operating system, okay? Until beginning of event and until the operating system start current job, that is the interrupt latency. You cannot avoid such an interrupt latency using the CPU scheduling algorithm. Okay? CPU scheduling algorithm will be activated after that. Okay? After that, it will take a time also to run your scheduling algorithm. That is called dispatch latency. Dispatcher is another name of the scheduler. So it will take a little bit more time to run that one. And so you need to consider what is the interrupt latency. There is no perfect real-time system. Real-time means no latency. Doesn't make sense. Okay? At least small amount of the interrupt latency as well as dispatcher latency. So interrupt latency is the operating system problem. How operating system is whether you have the fastest bus or whether operating system is an operating system issue. But you can reduce the dispatch latency by considering the simple algorithm. Then how can we do that? Any real-time operating system, real-time CPU scheduling algorithm must consider priority. Okay, priority is the also. There might be several events in the vehicle-to-vehicle sensor. Okay, right? Sometimes just the temperature. Okay, additional information. But sometimes how close, and even 10 meter and 100 feet or 50 feet and 10 feet. But within 3 feet, that is critical, so you need to do something. So there is different priority. So based on the priority, most of them are based on the priority. And also, this is some of our previous process list is just the limited number of process. What about the real operating system, real life system? It's a kind of a stream. Keep coming. So we can consider such a process as a periodic event, periodic. So then periodic process. So one period of time. Then T means is the assigned time. If the CPU select the process, it's like the time quantum in round robin. So required within this period, this amount of time should be given to that process. Okay, D means deadline. So for example, period is 10, it needs a 2 time slot, but deadline is 5. Within 5, in the period, this process should get at least 2 time slot. However, if a scheduler select this process at time 4, they cannot meet the deadline. So it is not real-time processing. So we will consider such a priority and deadline in our algorithm. So first one is a rate monotonic scheduling. So rate monotonic scheduling consider the priority as the period time. Shorter, small amount of the process periodic is the highest priority. Okay, and on the however, the longer period the process is the lower priority. So shorter will be selected. For example, suppose that we have the 2 processes. The process 1 has the period of 50. Let's say this is a millisecond. Within 50 milliseconds, process 1 should get how much? 20. Okay, 20. So process 1, the periodic is 50, and process 2 has the 100, the periodic, and the time required the 20, and process 2 is 25. At that time, P1 is a shorter period, right? So higher priority, so it will be selected. Then followed by P2. P2 in this case is a 25 or 1, 2, 3, 35. This is a 35. So P1 is selected. Then, in this period until 50, P1 does not need any CPU time. So P2 will be selected up to 30. Even though 30 is not enough, still remainder 5. At this time, CPU scheduler will select P1 because this is the highest priority. So select this one, then P2 still have the time because P2's the period is 100. Until 100, it can be completed. So P2 will be selected over here. And same thing for the next period. So this one, so we can meet the deadline for process 1 and process 2. So this is called the rate monotonic the scheduling. At this time, we consider the period, the amount of time for the period as the priority. Sometimes this rate monotonic scheduling cannot meet the deadline. Like in this example, let's say the P2 has the 80 instead of the 100. At that time, because of P1 should be executed, the P2 cannot be completed within the period time, cannot meet the deadline. So, because rate monotonic, just consider what's the size of the period. So that is just the priority. So to address that problem, so our goal is meet the deadline, right? That is the priority. That is the important thing. So always the deadline first. Scheduling means which one will have the earliest deadline. Which one should be executed first? Which one? That need should be completed earliest deadline. So that is the earliest deadline first scheduling algorithm. So for example, at this time, which one is the earliest deadline? P1. So P1 is selected. Then P2, okay? At this time, P2 is here, so P2 can still keep the CPU resource. And time 60, which one is the earliest one? Okay, P2 is the next time, 160. P1 is over here, so P1 will be selected. Then P2 and so on. So we can check. At this time, there might be no problem. All P1 and P2 can meet the deadline. Okay, that is the EDF, the earliest deadline first scheduling. Proportional shared scheduling is we can depending on the period, the length, so we can proportionally give the CPU time. Okay, so we are not going to see the details of it. So POS6. So each operating system uses different scheduling algorithm. Most of them use priority based. Not most, every operating system use priority based, but what kind of priority use? So Linux recently used the 2.5, the kernel version, or 2.6, they use the priority. And is a preemptive, which means it will be stuck in the middle of the processor, so it's a priority based. Windows long time used 32 level priority, but as I said, it's usually used 15, the priority for application port. And the other, the 16 to 31, will be used for the real-time class. Class means the priority level, kind of priority queue. So the other upper, the higher, this priority will be used for the real-time. For user application, it's usually 1 to 15, the 15 different levels of the priority. And Solaris has the different classes. So like this one is also priority-based scheduling algorithm. Even nowadays, there are new scheduling algorithms are coming in. The most popular nowadays is real-time scheduling because we have a lot of the firmware or embedded system that requires such a real-time scheduling. Once we have such an algorithm, we should be able to evaluate which one is better, which one is not better. Then how can we evaluate the algorithm? There are different approaches. So this is not only for the CPU scheduling algorithm, it's any operating system algorithm can use such an evaluation technique. There are 4 evaluation techniques we can use. The first one is deterministic modeling. What is a deterministic modeling? Deterministic modeling means, as we have used so far, what did we use to test the scheduling algorithm? Process list, right? We have the process list, P1 alive the time 0 with the CPU burst time 10, P2 alive time 10 with the CPU burst time 5, something like that. Then with the process list, we test with the first come first serve, we test with the preemptive, the shortest stop first, and see which one has the lowest average time, something like that. So that is the deterministic modeling. Problem of the deterministic modeling, sometimes it's hard to have such a process list, process model, okay, realistic process model. So, but benefit, it's easy. Without implementation, we can test it and we can evaluate. This one is better than this one. And queuing model is used for even the network. So we actually make the mathematical model. Okay, it's kind of waiting to enter the running queue. Okay, so can we make the mathematical model? So that is the queuing model. Queuing model is used for marketing also, like in the McDonald's. So for example, the McDonald's would like to open the branch at UB, then they should guess how many customers are coming and what time, how many employee we need. So hourly employee and 2 or 3, and how many counter will be opened from each time slot. They can make the mathematical model, and it will be usually exponential distribution. So if you are interested in such a thing, you can take I'm not sure whether we have the queuing, the theory, the class. I don't think so, but some of the mathematical department offers such a course. This queuing model is used a lot in the networks. And also, measurement from implementation is, why don't we implement using the programming code? Okay, why don't we implement the CPU scheduling algorithm only? Okay, then test it. The last option is implement entire operating system with a new algorithm. Then run whether it works or not. Okay, so a problem is costly. But if it's not working very well, we need to throw away. So it's a waste of money and waste of time, but it's a realistic. So very mission critical system, you need to do the real implementation. Okay. Those who are interested in the implementation, why don't you go to this website? This is a Java applet, so you can test the different algorithm, the CPU scheduling algorithm. Any question? Okay, so as I announced, before we start, why don't you be ready? Homework. If you go to the exercise 6.15, let me check again whether it's correct. I want to double check. Okay. The exercise 6.15 explain about the regressive round-robin algorithm. You don't have to solve the problem, okay? You can understand what is the regressive round-robin problem from the 6.15, okay? 6.15. Explain. This is the 9th edition. 6.15. Explain. Describe the regressive round robin. Then there's the you need to solve the problem of the 16. 16 actually you need to solve the first come first serve. Shortest job first. Shortest job first. And non-preemptive priority and round robin. Okay, round robin 1. I think round robin 1. Plus regressive the round robin. Okay, you need to solve the this plus regressive round robin. And option is time quantum size 1 incremented by 1 and maximum time quantum is 5. Actually, the idea of regressive is the next round. Why don't we increase time quantum size? It starts from 1, then next round it will be 2. Next round 3. Next round 4. It will be eventually 1. First come first serve algorithm. That is called the regressive. Why? Regressive means it's kind of convergent, try to meet. So that is the time quantum 1 but incremented by 1 and maximum 5. So this is the 6.6a, then C and D. You don't have to solve the problem B, C and D. It's a waiting time and response time. So you can check which one is better, which one is so do not solve the problem 15. 15 is for understanding regressive round robin. Then solve the problem 16. Okay, that's the question. By October 7th, next week.
Briefly explain how you're gonna work on the project 1. So project 1 can divide it into 2 parts. First one is how to create a child process using C and creating a selection feature also using C. So this is how I generally summarize some procedure that you should go with. First, you have to print a prompt. Prompt is like when you open the virtual machine. There's in the description of the lab in the project, it's like UBOS. So each time you get, before you get input, you should print this. So that means your program is running. So after that, you have to import your command. So it's like you want to list something, or you want to make directory, something like that. It's all from the program. So after that, you have to not only you get input, but also you have to parse it to tokens. So that's why, because in the for procedure, you have to use the exec family function to execute in the child process. So you have to parse, because when you get the input, like if you your command is like list or, so when you get input, it's like a string. So you have to parse it into tokens. So the first one, this is the second one, it's like that. So the exec family function can work. So the third is like you have to use the fork system call to create a child process. So as you all know, when you use the fork, the system will reply two values. The first one, if it's greater than 0, so it means the parent process. So if it's equal to 0, it is the child process. So in the child process, you have to pass the tokens you already passed to the exec family function, so you can run your shell program in the child process. So the parent process also have to do something because when you run the exec family function, you will get a result. At the same time, parent process is running too. So even if you run the list command, so this child process and parent process will run together. So if the child process is running slower, so it's like when you type last, even you don't get the result, the parent will keep going, so will print another prompt. So that doesn't make any sense. So the parent have to wait the child process to be terminated. So there's a wait function you have to use in the parent process to check whether the child process is terminated or not. So if the child process is terminated, so you go to loop again, so the print prompt will get into input from the user again. Also, if the user imports the exit command, so the program should be terminated. So there's the while loop, you can check whether the import is exit or not. And if the user input the selection, so you will go to the selection part, the second part of this project. So I'll give you a skeleton code. It's like this is in the main function, there's a big loop, so you can run on. So this is a flag. So if you input this X, so this flag will be false, so they will terminate the whole program. So the first one, you have to print the prompt. So it's like you was. So you wait the user to get to put the input, then you parse the input. So then now you will know the input whether it's X or selection. Then you will get some check. After that, you have to check. After that, you have to use the fork function to create a child process. Then you can see. I think in the quiz 2, you got some code from the use fork and function. So you can check whether this is a child process and parent process. And in the child process, you have to use exec. Now I use excvp function. Then you can use whatever you want from the exec family function. And after you run that, the parent process also have to wait the child process to be terminated. So after the child process terminated, then print the prompt again. So that's how the project one, the first part works. So this is example of fork. Then after that, I will show this demonstration in the virtual machine. So I will briefly explain that. So you create argument. So because I use execvp, so the first parameter is the all the tokens. I think it's the path of the command. The second one is the other pointer to the tokens, because in this example, I just want to, I just assume that the user just input ls, want to list something. So the first parameter of the argument, command average will be ls. And I use fork. If it's smaller than 0, they will print arrow. If it's equal to 0, it means it's in the child process. So you have to print this child process, then run your shell program. If it's greater than 0, so it means it's in the parent process. So you have to wait. You create this. You use this wait method to wait the status. This status is any child process signals like that. So why it's smaller than 0, that means the child process is not terminated. So this will be an infinite loop until the child process is terminated. So that's why I print this is end of fork, then back to the beginning. So this is only the example of fork. I don't want to write anything about prompt. So I will run a little bit example of this using virtual machine. So I'll delete this file first. So now you can see in this directory I have a fork.c. This is a C file. So I'm going to just check that. So it's the same as the example I just showed you. So if here I want to input the list command. So if you want to compile it, use GCC, then file name. So that means it works. So you can check, you can use list. You find there's an a.out. Defaultly, you can see that. Defaultly, if you just use GCC, not some option command, it will show just a.out. If you want to get the output from some specific name, you can use fork, O, whatever name you want, exe. So use list again. You can see there's another exe file. So defaultly, it will, the output is a.out. So after that, you have to run it. So you can see there's a child process. This is when the system returns the PID to 0. This will print it. So this means it's the child process. At the same time, they will reply another one. There's a parent process. And as you remember, in the code, the parent process have to. There's another command. There's another command, print this end of these fork. So, but before that, you have to wait. So no matter what the child process is faster or not, you can see this statement will print after the child process finished. So that is how the fork should work. And also give another example, if you type another list or, it will show this result, right? Let's just change a little bit of the code. So now the tokens will be 2. So I just this means these are 2 tokens derived, because when I get the import of the input of the user should be list or. So this is the one string. I want to take 2 tokens like ls. The second one will be LO. So I will compile again. 641. So when you run it, it will show the same result, like you type directly type ls and or in the command terminal. So after that is a selection part. Selection part, most of them is the same. You have to print the prompt. Then if you check the input selection, also you have to fork to create a child process. Then in this situation, I use some fine shell program that you can get find all the executable files, because in the requirement you have to list all the files in an alphabetical way. And not only in alphabetical way, you have to show the order of this executable file, 1, 2, 3, 4, 5. This is why, because after you list all the files, you have to get input from the user. Then if you type 1, that means you have to run. You want to run the first file. So also, you have to get some handle some basic error handling. It's like if you don't have something executable file, it will show that there's no executable file, something like that. So this is also same example.
Do you have to an input for each file is also for the numbers? So,
Yeah, you have to put name and numbers.
Yeah, so we cannot terminate the child, right?
Yeah, if this is all in the child person, you can see.
Okay.
After you run that, so this is all in the child person.
Yeah, it's like
So the above is the same as the pretty child process. So if you use the selection features, you have to use a command like find something, so then run exec, then list.
Yeah, I know.
Right.
The read username. Yeah.
Right. Then run that. Then parent will wait if the child process is run, the process is terminated. So back to the beginning.
So once we execute the like number 1, so after we execute that A that out.
Yeah. That's the correspond. Yeah. That's means 1 is 1. And also you have to.
So you got to add that slash then the name.
Yeah, I think so. Yeah, because the past. That's pretty much of the project 1. If you have some question, okay, you can email me or send a message to me.